On so today's lecture, right? We're going to continue our discussion of cryptography. So we've started to talk about block ciphers. We've talked about confidentiality and integrity. So we're going to continue with that. I'm going to do some slides today, a little bit slides, so summarize some of the topics that we've already covered, and then throw in some new ideas. Okay. And then we're going to, after the slides, we're going to start drilling down on specific things. Yeah, so that's the plan. So I remind you, we're on week 4. This is week 4. So you can expect an exam on week 6, right? Exam number 1, it's a written exam about these concepts that we've looked at so far. And we've talked about that, right? So we've addressed secret key encryption. We've addressed substitution cipher. We addressed the XOR hash algorithm last week. And then this week, we're going to continue with hash algorithms. So we're going to do the OpenSSL portion of this lab. So, computing an MD5, SHA-1, SHA-256, and all of that. And various other problems like corrupting, cipher. So you looked at a simple algorithm last week, and this week in the lab on Thursday, you'll be solving some problems, just using basically cryptography, I should say. All right, so I have slides, every now and then. So let's take a look at these. So it should be this one. And it's several topics. So I kind of motivate some ideas with this, and then we'll start specifically getting into them. Okay, so there we go. All right, so cryptography. So this is the second set of slides that I have. So remember, we're framing these problems in terms of the principles. Cryptography provides the building blocks to achieve, security, network security, for instance, a lot of what we're doing. So privacy and confidentiality, you should understand that concept already very clearly, because that's what we've been doing. Integrity is the other one. We're kind of looking at that, integrity, last week and this week. Authentication is coming up. So we haven't covered authentication and how cryptography can achieve this. But today we begin that discussion. And that's a very, I would say it's actually like the bulk of this class. A good, maybe half of the class is authentication, is where it's a little bit more complicated and so on. Non-repudiation is a similar concept to authentication, right? That you can't deny that it was used. So it has to do with, originator and unauthenticated originator. All right, so symmetric encryption. So I'll talk about all 3 ideas today: symmetric encryption, and integrity with hash functions, and then asymmetric encryption. I will just start to lay the foundation for that, but kind of asking some questions and things like that. So symmetric encryption, the universal technique for providing confidentiality for transmitted or stored data. This is what we use today, right? To achieve confidentiality, to send your movie via Netflix and all that, because it's efficient. We've talked about the XOR operation underlying. We've talked about, block algorithms, etc. And so that's really, what we are going to use. It's the universal technique for providing confidentiality. That's a very important statement. All right, also referred to as conventional encryption or single key encryption. So remember that the problem with this so far is that we don't know how to exchange the key. And so that's what we're going to start motivating as we move forward. So 2 requirements for secure use. We need a strong encryption algorithm, right? So for instance, we'll talk about the 2 symmetric encryption algorithms, DES and AES. DES has already been broken, and basically then, we'll talk a little bit about that historically, and then AES, but you will see DES around in some places because you can still use it. It just depends on how sensitive your data is. So the two requirements, need a strong encryption algorithm. The other one is the sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. All right, so here we have a diagram, a simplified model of symmetric encryption, as you can see. So the idea, we have, you can see my mouse, maybe not. You have the plain text message there, right? And that goes into an encryption algorithms, such as DES, for instance. We need a secret key shared by the sender and recipient, right? And then we're going to perform some kind of an operation, a secure operation or secure algorithm. And then once we've done that, we send the ciphertext or the encrypted message, basically. Then on the receiving, so that's Bob, and then on the receiving end, Alice, we'll have a corresponding decryption algorithm, which is a reverse of the encryption algorithm. With the same key and the cipher, you will produce then the plain text message, right? So that's, the key concept there. All right, so attacking symmetric encryption. So this is, something fun that you guys can do for the term project. Certainly, as we start moving forward, we'll do at least 2 or 3, problems about breaking encryption and the techniques that are available. We'll certainly, if we had a quantum computer, right, we would be able to break RSA, for instance. And we have a quantum computer, albeit a simulated, not a real. All right, so but I'll show you guys the KISS-KIT framework, and then we can use that basically to do such a thing. All right, and then we'll talk a little bit about how, what is the underlying reason, right? Why we can break it, but to understand that first, we have to understand how RSA works. So we're going to spend a lot of time thinking about how RSA works. And then, thinking of the techniques, or what are the weaknesses. But that aside, the common attacking techniques for symmetric encryption would be things like cryptanalytic attacks or brute force. So cryptanalytics is basically there's patterns in the data, right? So we've seen substitution cipher had a very clear pattern. We literally had an equation for it. So it's a bad cipher because of that. So it exploits the characteristics of the algorithm to attempt to deduce a specific plain text or the key being used. If successful, all future and past messages encrypted with that key are compromised. So I like to make a comment here about that last bullet. If successful, all future and past messages encrypted with that key are compromised. So there's a thing that you guys probably don't know, or maybe you do know. But I'm going to tell you, and it's, it's something that's going to it might surprise you. So 2 things. We have secure communication, right? You've sent a lot of emails, probably since you were in high school, I assume, right? So decades, almost a decade, right? You've been communicating. You have a huge Gmail. All of that is encrypted, thankfully, right? So you've communicated, you have, your files are encrypted, your whole social media communications are encrypted, maybe your text messages, all of that, right? Right now, the US government has basically said that all that information has been intercepted by other parties. And they have it. It's stored in a bunker somewhere. But it's unencrypted. It's encrypted. Sorry, it's encrypted. So all your personal data of your entire life, right? Everything that you've ever written, everything, at some point has been captured. And it's somewhere right now, sitting in a bunker or a bank or somewhere there. It's encrypted, but it's just waiting for the day, maybe 15 years from now, maybe 10 years from now, when they will have the technique or the quantum computer that will break all of that cryptography. So I don't know if you've ever thought of that, right? So you think you're secure now, and you are, as far as we know it, We are. But every government in the world has probably done this. So the US has probably done this to other countries. So everyone is, because why? Because there may be some important information there, right? So, you know, maybe some planning, some organizational things, or however governments work, all that information, you know, is communicated, has been encrypted. So some governments figured out, you know what, let's just get it now. It doesn't matter that we can't break it today. We may be able to break it 10 years from now, 15 years from now. So that's a serious concern. Think about it, right? Because in 15 years, if they find a way, like with a quantum computer, if those ever come to be an actual thing, or with other AI or something, if they break all of those ciphers, old data becomes known. So anyway, so deal with that. All right. But yeah, but this is a true thing. This is like absolutely the truth. All right. So you know, governments are always capturing information to get an advantage base. All right. So anyway, so that's cryptanalytics. So as I said, if successful, all future and past messages encrypted with that key will be compromised. And that, you know, that's a true statement. You know, DES, for instance, has been broken already, right? So we already have an example of this. Maybe things that were done in the 80s, etc. There was some information there. It was broken. Some governments or whoever it is may just want to run computers all day, breaking things and trying to extract that information. All right, the other one, of course, is brute force. We'll talk a little bit about brute force. Try all possible keys on some ciphertext until an intelligible translation into plain text is obtained. This is probably not a good idea to do, right? And we'll see why. But, you know, computers are getting more powerful and things like that. So the solution for this one is basically make your keys longer. The longer a key is, right, the more permutations of that key, the harder it is. So the last time I checked, for instance, you know, a password that has 4 characters can be cracked in a reasonable amount of time, but you add that 5th character or that 6th character and it becomes harder, right? So just in terms of permutations, I'm not considering known passwords. Like if you use password 1, 2, 3, 4, 5, you know, they may break that. All right. But anyway, so yeah, so these are the techniques. And then there's specific techniques like for RSA, there's something called factorization. We'll discuss that. There's some very interesting things getting into, you know, the math of how the algorithms work. So here we have average time required for exhaustive key search. So as you can see, the bigger the key size gets, the more time it takes to like try all the possible combinations until you find the correct one. So if you look at, I can't even say, you know, how many years that is, but it's something 10 to the 18 or something years, basically. Okay, so this is the so it's a difficult thing to do. So not a great approach, right, to brute force encryption algorithms. Okay. All right, 2 of the most important techniques, and remember these are basically documentation, right? So these are actually like the framework, not the implementation itself. So there's like an actual document, you know, an ISO that basically establishes, okay, this is the algorithm. It should be like this and this and that. Everything is known. And then there's going to be many companies that will go ahead and implement it. And they call it like Swordfish or Bluefish. You know, they give it their own name. But so the most important techniques in symmetric encryption were the data encryption standard. That's actually the most studied algorithm in history, right? So, and then we have AES, the advanced encryption standard, and they are both block ciphers. So you already know, because we started doing the XOR hash algorithm, you already know a little bit how to implement this, right? Because we started to do that. The next step that we're going to do is take that XOR code, and instead of generating hashes, we're going to start to do encryption and decryption, and then add a mode of operation, and then I will give you the algorithm for the data encryption standard. Okay, I don't cover the algorithm in AES because you will see that the DES is already quite complicated to implement, and it's not even secure anymore. So AES, it's a little bit even, it's more challenging. All right. So just some ideas. So basically we had DES, triple DES, and AES, which is, the secure algorithm used today. Triple DES was basically just like a workaround when DES was broken in the late 90s. People just said, okay, they broke DES, but it takes an hour, let's say, to break it. So what's the simple solution? Let's just run it 3 times, and now it takes 3 hours. Do you see that? And so basically that's what triple DES is. It's literally the same algorithm, just done 3 times. And then a few parameters are changed. You can see the block sizes are 64, 128. The key size is 56. It goes all the way to 256. So you can see, as you have, initially you didn't have enough computing power, right? When these algorithms started, so things had to be smaller. And then as you move in time, you have more. And you will do an exercise in one of the labs where you actually have to try different key sizes. You'll try as big as 4096 key size. And you will see that that significantly takes longer to encrypt than something smaller, right? So remember, performance is always a key aspect of encryption. All right, so data encryption standard, as I said, the most widely used encryption scheme is referred to as a data encryption algorithm, uses 64-bit plain text, 56-bit key. Concerns about the algorithm: it was the most studied encryption algorithm in existence. This is important because remember that you don't achieve security through obscurity. What that means is you don't achieve security by just creating an algorithm that nobody knows about, right? In fact, these algorithms are really well known, right? And even though they are studied, and even though everybody knows everything about them, they're still secure as long as the key is kept secure. Does that make sense? So there's nothing there that you have to keep a secret about the algorithm, but the key, obviously, as long as you keep that secret, you're secure. This is the key insight that we have with these. And so these algorithms are studied extensively because obviously all of our banking, everything basically that you do in the modern day has to do with encryption. So it's really important. The EFF announced in the late 90s that DES was broken, basically. And at that point, then, a call came for a new encryption standard, which is the advanced encryption standard. Here, this is a graph that just shows the time to break the code. So you can see it's kind of a linear relationship between the number of years in some scale and the key length. Okay, so the key becomes bigger and the algorithm becomes more secure. So today, some people would argue that they're concerned about the current state of encryption because of, as I said, with quantum computers, which is what I will show you. And so there's a lot of, right now, the area of research in cryptography, if this is something that is of interest to you, is to move to what is called post-quantum encryption algorithms, or another way, a better way, is quantum-resistant cryptographic algorithms. Now, keep in mind, there are no real functioning quantum computers right now that can break encryption. They don't exist yet, right? But theoretically speaking, a lot of people have proven there's something called Shor's algorithm. You can look it up on, it's very interesting YouTube video. And it's basically an algorithm by a gentleman, Shor, that breaks encryption, but it has to use a quantum computer, right? So it has to use those techniques. And so obviously the government is really worried about that, given that, everything depends on that. So the research, the funding currently is going to try to create algorithms that would be, as they call, quantum resistant, okay? And people propose algorithms all the time. You hear there's 2 or 3, and then it's like, oh, they work. And then some university is like, oh no, we broke it. So it's a challenging thing and it's an ongoing thing, but it's very interesting. So that's where we are right now. All right. So there's like there's maybe a need to start worrying about that. Anyway, so that I said that because this takes us to triple des. So triple des was like, a temporary solution when they broke des, right? So basically it repeats des algorithm 3 times using either 2 or 3 unique keys. So that's the key thing, that there's, you have to use 3 keys now because you're running it 3 times. So you can change the keys, and that, makes it better, because now instead of finding 1 key, they would have to find 3 keys. Yeah, so it's obviously that made it inefficient, as it was not designed to do that. But the underlying algorithm is still des. All right, then historically, that took us to the advanced encryption standard, AES, current state of where we are. Needed a replacement for triple des. Triple des was not reasonable for long-term use. It's still, but when so the NIST, right? So it's the Institute of Standards, right? And so basically they create a call for proposals for a new, what they called an advanced encryption standard, something that could be more secure, right? And so this, happened in the 90s, and so should have a security strength equal or better than triple des, significantly improve efficiency, so faster. Symmetric block cipher, for the reasons that we've already stated, that allows us to achieve confidentiality, and larger key sizes for obvious reasons. Okay, so this was proposals went out, and then many institutions or whatever companies proposed, and that one was accepted, and this was published, right, by the institute. You can look it up, right, and this is what people then rely on for their implementation. So then IBM, Google, all these companies will try to implement their own versions of this. Okay, now keep in mind, the algorithm is proven to be secure, but that does not mean that the implementation is secure, right? In fact, some companies could intentionally not implement it correctly to have, backdoors into things, right? And just hack the algorithm, right? Microsoft might do that because, we all live in that space of Windows and so on. Any questions? Does that make sense, guys? All right, so that's a little bit of the history, right? Just to kind of give you the big perspective. So these are the block ciphers. Now we're going to look at the problem of RSA, right? I like to start with this because really this is why I make it require that you guys work with a partner in this class, because as we start looking at RSA, etc., we just have more things going on. There's going to be 3 keys per person now instead of just 1, because there's going to be your public key, your private key, and then the symmetric key that you're exchanging, right? So it's going to get more challenging. So we're going to think of a scenario always where we have the classic in cryptography Bob and Alice, and I'll use the term Zelda to be the person that's trying to intercept. All right, so we're going to think of that, and we're going to be exchanging messages. Okay, this is a cartoon. All right, so first we're going to look at some of the properties of symmetric encryption, what it does, what it can't do, and then we're going to start to motivate the ideas of, how do we solve it. All right, so, and then from that, we're going to move on to more specific things today. All right, so the properties of symmetric encryption. So pros, as you know, so I'll use it in terms of Zelda. And so pros, confidentiality, right, of symmetric encryption. Zelda cannot access the message without knowing the key. You guys that should be clear in your minds. Authentication, only whoever knows key can participate in the communication. So it's a type of authentication, right? Although we want to be more precise with that authentication, right? Integrity, if the message C is modified, it will decrypt to gibberish, right? So there's that. The cons, though, of symmetric encryption are that key distribution is critical and requires out-of-band communication, right? That should be clear to you, because this has been a problem that we've been working through all semester, and you don't yet know how to exchange that key. If the key is compromised, that can impersonate both Bob and Alice, and that's not good either, right? So it starts to get into authentication, and it cannot be used to prove that a message was sent by specifically one of the involved parties. So that's why we want to have specific keys for everyone. So in this class, very soon, everyone is going to have a public and a private key. And with that, I will, if we wanted to communicate through that, I would know exactly who everyone is and what, who is the originator of a piece of information. Okay, so that's the key aspect. All right. So practical issues also. So typically, symmetric encryption is applied to a unit of data larger than a single 64-bit or 128 block. We've looked at the modes of operation, and I will drill down into that more today. So that one of the specific aspects. So I just wanted to bring this up again. Remember, electronic codebook, ECB. You guys already know that this was insecure, right? So we'll talk about that today as well. So electronic codebook, ECB mode, is the simplest approach to multi-block encryption. Each block of plain text is encrypted using the same key, and cryptanalysts may be able to exploit regularities in the plain text. So this is the square and circle that we saw before. So the modes of operation are alternative techniques developed to increase the security of symmetric block encryption for large sequences, right? So we will look at that on the whiteboard in a little bit. So just to remind you that ECB is that, right? So the squares or circles here, do you guys see a pattern in the encrypted image? You do, right? You do see the hair. And because you see the hair, you're able to infer this from the cipher. You can infer something about the message, and that's the definition of an insecure cipher. So don't forget that, right? So that's the key thing. You should not be able to say anything. All right. So we've talked about, so I'll come back to this. I want to get to this part. All right. No, sorry. Yeah. All right. So we're talking about symmetric key encryption, right? And we've talked about the key. So now I talked about the pros and cons. And now more specifically, what are the limitations of symmetric secret key encryption? So obviously the key, right? So the fundamental limitation of symmetric secret key encryption is, how do two parties agree on a key? Do you see that? So that's the next big problem that we need to address. In order for Alice and Bob to communicate securely, they need to agree on a secret key. But in order to agree on a secret key, they need to be able to communicate securely, right? So it's a so-called chicken and egg problem, right? Which one came first, right? So this is the issue, right? Okay. So this problem is actually really important. So we've solved it so far by saying, we're going to meet at a coffee shop, exchange the secret key, and then travel and so on, right? And yeah, we solve it, but that doesn't work in the digital world, right? In the digital world, you can't call Amazon and say, hey, let's meet up in a coffee shop, and then call your bank and, and what if you want Etsy or, some new thing that you've never used? You can't do that, right? So for the internet to work, this had to be invented. Very important. So you guys have heard of PayPal, right? PayPal, PayPal was basically several companies that solve encryption to make payments, right? So they dealt with the banks, and then they also did encryption, and these, all the people that created these companies then merged them together to create PayPal. They all became super rich, uber rich. Elon Musk was one of them. They're called the PayPal Mafia, right? So all these guys, Peter Thiel and a whole bunch of other people, they became, super successful. And it's because they solved literally this problem, right? So look it up. It's really interesting. All right, so this problem is especially common in the digital age. we constantly end up at websites with whom we decide we want to communicate securely, such as to make a payment, right? So we go to a website, you want to make a payment, you want to send some secure communication. So we want to communicate securely like online stores, but with whom there is not really an option to communicate offline to agree on some kind of secret key. In fact, it's usually all done automatically, browser to server, right? And there's really a lot that's going to go into this. So today I'm just going to give like the overall idea, almost like at a very fundamental level. And then we just have to think how that is expanded to become, the actual solution, which involves certificate authority, certificates, and all of those things that we're going to talk about a little bit later in the semester. So in fact, it's usually all done automatically, browser to server. And for the browser and server, there's not even a concept of offline, right? They only exist online. That means client and server just means the server is basically Amazon, right? Their web server, that's very clear. And the client is what? Your laptop. And what specifically in your laptop is the client? The browser, right? So your web browser is really where your keys are stored, right? And all that. So we're going to look at that later in the semester as well. So we need to be able to establish secure communications over an insecure channel. Symmetric secret key encryption can't do this for us. We'll use symmetric encryption to send the message, send the payment encrypted, but once we've exchanged a key, right? So that's where asymmetric, or also called public key encryption, or PKI for public key infrastructure, or RSA, which is the underlying algorithm, that's where we come up with the solution. So in asymmetric public key cryptography, both communicating parties, okay, i.e. Bob and Alice, or Alice and Bob, have two keys of their own, okay? Just to be clear, that's 4 keys total now. And there will be a 5th key, right? Which is the one that is exchanged using these approaches. In fact, you should be aware that asymmetric key encryption is not used to like encrypt that Netflix movie you'll watch, later this week, or your TV show, right? That because asymmetric algorithms, or RSA, are actually much slower than block cipher algorithms. So it would be very inefficient. Also, it's not really meant for that, but it's meant for small things like a key, right? RSA is meant for small things like a key. So each party has their own public key, which they share with the world. Basically, it's called a public key, and their own private key, which they will keep private. And they will keep it basically as a closely guarded secret. So I can tell you right now we're gonna get to a point where we're gonna create these little files. So you'll create a file called your public key.pem file, and it's just a text file, and then it'll have some information, including the key, and then we will have your private.pem. So 2 files are going to store this information. This is how SSH works. So we'll follow this approach, and that, that's basically how it's going to work. Okay, so we'll see that later. But initially, we may just do it in a more simplistic way. Any questions so far, guys? Okay, making sense? All right. So asymmetric public key encryption, the magic, which really, this is like one of the algorithms I admire the most. It's very like amazing, in my opinion. So the magic of public key cryptography, right, is that a message, think about this, right? The magic of public key cryptography is that a message encrypted with the public key can only be decrypted with the corresponding private key, right? So you guys will learn that you will generate a public key. It's like a number. Everybody has that. And from that, you're going to generate a private key. And then you will learn to use those together, right, to achieve various things like confidentiality, authentication, and so on. Okay. Alice, for instance, so again, we're going to talk about Bob and Alice. So Alice will encrypt her message with Bob's public key. Okay. And even though Zelda knows she used Bob's public key, and even though Zelda knows Bob's public key herself, she is unable to decrypt the message. So she has that key, but she can't break it. Only Bob, using his secret key, which in this case is the private key, can decrypt the message, assuming he's kept it secret. So you basically will go in the terminal or some program, you'll generate two keys, your public and private. You should call it, Mary Smith public, Mary Smith private. You can put your Mary Smith public like on your website or your favorite Twitter or something. Yeah, Twitter, X. And then, but the private key you need to keep just for yourself. Okay. And then this way you can communicate with anyone in the world securely. Questions? No questions? All right, so let's take a look at a diagram here. So I have these special effects. All right, so basically we have Alice and Bob, right? Okay, Alice and Bob, and they want to communicate. So right now they're sending a plain text message, which could be a short little message, but in general, as I said, we want to use this mostly for key exchange. And there are other key exchange techniques, by the way, as well, but RSA is the better one. So Alice will create her private and public key, and then Bob will create his public and private key. They have a plain text message, which needs to travel through the unsecure internet, and Zelda is going to be there snooping, right? And so the plain text is going to be encrypted with an algorithm, a specific algorithm, such as the RSA algorithm, but Alice will use Bob's public key. Do you see that? Because she has access to it. And that message, once it's encrypted with Bob's public key, it cannot be decrypted at all. Like you can look at it, you can try whatever you want. You cannot decrypt it. Only, so then that generates a ciphertext, which goes across the internet, and then that ciphertext then, to be converted back into the plain text, it needs to use Bob's private key. Does that make sense, guys? Any questions? What would happen if I use my private key? Let's say I'm going to use names. So Alice has a message and she encrypts it with her private key. You agree that if she takes a plain text message, right, and she encrypts it with a private key, it's a cipher. So it's definitely a cipher, right? And she puts her public key on the internet and she puts that cipher. Do you think that's useless? What do you think about that? Does that make sense, what I'm asking? Do we achieve anything with that? Is it a way? Is it secure? Let me ask you that. If Alice takes the plain text and encrypts it with her private key, and now it's the ciphertext, does that achieve anything? Is that secure? Why not? She put her, yep. So so then Zelda can grab her public key, right? And decrypt that cipher and obtain the plain text, right? So it's not secure? No, okay, good. Yeah, it's not secure. Is it useful in any way? It seems kind of right. Can you think of something that could be useful about that idea? What's the only thing that can decrypt that cipher? Well, she used a private key to generate it. Her public key. only her public key. Can Bob's public key decrypted? No. Okay. Is there something, some usefulness to that? You know that that's Alice's public key, right? You know that. Like she gave it to you. You hold it in your hand. You've never exchanged it. So you know this is Alice's public key. And I just got a message, a ciphertext. And I decrypt it with Alice's public key and I get the plain text. So what does that tell you? It's not, there's no confidentiality there, but it does tell you something.
It's a cipher. Specifically her private key.
Yes.
Specifically her public key. It only works with one each other.
Yes.
So it's its own specific cipher.
Yes.
That's all I can think of.
Right, but there's something there, actually. Think about it. You're almost there. Only her public key. She gave you. She's like, this is my public key. Hold this. Someday I'm going to send you an important message. But other people send you messages. What's going to happen when those people send you messages? You cannot decrypt it. But one day, she'll send you that message, that cipher, and you will use her public key and boom, you'll get the plain text. So what does that tell you? What does that provide? Yes. She gave it to you. She gave you the, it doesn't matter where the cipher comes from, right? Because you do have her public key that you're holding right here. So that all those ciphers, none of them decrypt except one, right? So what does that tell you? Of a million ciphers that you got, only one decrypted. So that one, and it decrypted with her public key. So what does that mean? That she used her private key to generate it, right? Because that's the only way that you can decrypt it, right? You can only decrypt something. You know, if you have Alice's public key, you can only decrypt that message if it was generated with her private key. And you know for sure she would never, that this is an assumption you have to make. She would never give that private key to anyone. So what does that provide? Which principle of information assurance does that provide?
Integrity.
Not integrity, authentication. Think about it. I know it's a difficult concept to grasp, but this is how we provide authentication. Do you guys see that? It may seem useless because it doesn't provide confidentiality, and that's usually what we're looking for in encryption, but actually authentication is really important too. Do you guys understand the idea? Yeah? Any questions about that? We'll come back to that idea. Yeah, please, go ahead. Yeah. Yep. Yes, this ties into that, but it's like those are wrappers to this idea. Actually, the digital signature just means that we're going to create, there's a file, we're going to create the hash of the file, and we're going to sign, which is basically encrypting that hash. Do you see that? Yep. And so it very good. So all of these are just the very basic primitives that start to get us to authentication. The same goes for the certificate authority, which a certificate authority is, you know how I grabbed this and I said, this is, you know, I'm Alice, this is my public key. We need that. And that's what something like VeriSign provides for you, because Alice literally, or Amazon literally goes to a company, sits down in a desk with executives of VeriSign, pays money, signs contracts, and then they say, yes, this key, I am VeriSign, a certificate authority, and I confirm that this is Amazon's key that you can use, their public key. You guys see that? So we'll see all these concepts in a lot of detail as we move forward, but it all comes from this one idea, the duality of the public and the private key. Okay? So that's how we'll start to see that we get authentication. So let's say that Bob is the teacher and Allison is the student. Bob is going to send an exam to Alice. You don't need to have confidentiality here, just authentication. So how do you do it? So from Bob to Alice, right? What's being sent is an exam, and you need to achieve authentication. These, by the way, are the exam questions. All right, so I'm going to give you a problem exactly like that. The teacher wants to send you an exam, right? Using RSA or asymmetric encryption, create the pipeline that achieves authentication of that exam. I may say also achieves confidentiality and authentication, but in this case, to keep it simple, I'm only asking for authentication. So how do you do it? From Bob to Alice. Plain text is the exam. What needs to happen here to achieve authentication? Oh, yeah. Let's go slowly. All right, so Bob takes the plain text exam and is going to encrypt it. Give a ciphertext, sends it to Alice, and then Alice does what? To decrypt it, right? So Zelda can also do that, right? Because she will also have access to Bob's public key because it's on his X or Twitter or whatever. But what Alice knows is that it came from Bob. So then she's going to work on that exam and do it because it's not like a prank or something. It's the actual exam. Do you guys understand? Yeah. All right, good. So yeah, I wanted to do that because some of the questions on the exam will be a little bit like that. Okay. All right. Any other, so I think this is, we're getting, yeah, that's the last slide of asymmetric encryption. Next lecture next week, we will do this same exercise, but then I will say achieve both confidentiality and authentication in one shot. So start thinking about that as an interesting idea. Okay. Because in this example of the exam, we only achieve authentication, but there was no confidentiality. The exam was known to everyone, right? Okay, great. So just a few last things. We're going to move on to modes of operations and hash functions. So I have a few more slides here. Yeah, so I think this was where we were. So modes of operation, as you know, they relate to block ciphers. So you can see here in this diagram at the top, that's a block cipher encryption. It is, in fact, the ECB or electronic codebook. Okay, we've established that it's insecure, but it's something we need to implement. And then CBC is also something that we're going to be implementing. Right. So basically, we take our message, we divide it into blocks. We have a key in symmetric encryption. We XOR it, and that gives us our cipher blocks. And then that's the encryption process. And then the decryption is just the opposite of that. Now, I'm going to throw in a new concept today, which is stream ciphers. Okay, stream ciphers are actually really nice. And they go back to the idea of the OTP. Hopefully you remember that, the one-time pad. What did we say about that? It was secure, but there was a problem. What was the problem? The key needed to be as long as the message. Remember that idea? So the stream ciphers are actually a type of a solution to that problem, where we now create a cipher as long as the message. So how do we do that? We have an algorithm. But what do we know about the key? The key needs to be as long as the message. Okay, we can do that with an algorithm. But there's another requirement for it to be secure, and that is that key needs to be 100% random. Now that we cannot achieve, right? So there's a compromise that we have to make in the sense that instead of using a random key of size equal to the size of the message, we're going to use a pseudo-random key. So we're going to have a pseudo-random number generating algorithm to solve this, right? And then once we do that, we can implement a stream cipher. Got it? This is a similar mechanism to your key fob thing that, you know, like every day when I log into Brightspace, I have to look at a number and punch it in. So it's a similar algorithm that's underlined. Make sense? All right. So here is the depiction of the stream cipher. Basically, the concept, you can see the terminology there. So pseudo random byte generator, right? Or pseudo random key, if you want to think about it in terms of the one-time pad. So basically, the key is this. It's very simple, really. You, instead of providing blocks of the message, now you're going to provide 1 byte at a time. Do you see what I'm saying? So it's like you take the message and you cut 1 byte and send it. 1 byte and send it. 1 byte and send it. And then what do you need? You need a corresponding algorithm that will generate 1 byte of the pseudo-random key. And so that's what a stream cipher means. Does that make sense? So you get 1 byte from the pseudo-random key, 1 byte from the message. 1 byte from the pseudo-random key, 1 byte from the message, and obviously you XOR them. And then you send, once you've done that, you send that byte. That's a stream cipher, basically. Any questions on that idea? Streams make sense? All right, so yeah, so you can see that there, here, right? So you have plain text met byte stream, right? And then you get, that's the message, but you get 1 byte of it. And then there's some key that goes into the algorithm. The algorithm is going to be deterministic, which we've established. Computers are deterministic, but it's going to have a seed, which is the random thing, which it can be like a key. Okay, and so the algorithm, we'll do this in Python also. Pseudo-random byte generator. So it just comes in and you XOR it. And then that cipher byte stream comes out, is sent over the insecure internet. And then on the receiving end, the same pseudo-random number generator needs to produce the key byte. The cipher byte comes in, XOR, to get the plain text original byte that you sent, and you've got your message. So as you can see, XOR once again is the underlying operation, and it's just a different scheme. But what important here is the pseudo-random function, which we will use a library to generate this. Is actually randomness is a little bit complex, so we won't get into that. All right. So a little bit about the comparison, block and stream ciphers. So block processes the input 1 block of elements at a time, produces an output block for each input block, can reuse keys. It's more common. The stream cipher, on the other hand, processes the input elements continuously, 1 element at a time, like a byte. It can be faster, less code, etc. So basically, those are the differences. Yeah, so that's the new concept. Any questions on stream ciphers? I could ask you on the exam, like, what's the difference, you know, etc. I would just say one sends blocks, the other one is 1 byte at a time, but they're both XOR. And the pseudo-random algorithm is important. All right, the last topic I think for today in the slides is message authentication. So going back to hashes, right? So we've covered all the topics of cryptography today that we've seen so far in this semester. We've covered confidentiality. We covered a little bit of authentication, and then we're going to talk about integrity once again. Remember that that's the focus of the lab this Thursday. So basically, message authentication protects against active attacks, verifies received message is authentic, content has not been altered from the authentic source. And this, as we have seen, can use block ciphers, for instance. And, you know, so we're also going to look at what happens when we corrupt 1 bit of the data. Here's the diagram, just to keep in mind how this would work. You will have to do this in this lab, work with a partner, and then achieve integrity, right? So what are you going to do? You're going to take some message maybe a text file or something. You're going to take in some message. You're going to generate the hash value, right? Using MD5 or SHA-1 or SHA-256. And then once you've obtained the hash, then you like append it to the message, you transmit it over the insecure internet. Then that's Bob, then Alice receives it. And what does Alice do? She's going to take the message, the light blue part, run it through the same algorithm, and she should then get a hash, and she's going to compare it to that hash. And if they match, then you're good, right? And that's something that an algorithm can do. Now, this definitely achieves integrity. Does this achieve confidentiality? This diagram here? Would you say? If I said true or false, maybe. Is this diagram achieving confidentiality? Or is it just achieving integrity? Or how could you make it achieve confidentiality and integrity? The key thing is what's being sent, the only insecure part, right? When you look at these things, is this part, right? Why is that insecure? Because that's the internet, right? So things are being captured. You can always assume that they can just capture anything that you're sending over the internet. So you agree that it achieves integrity, right? Does that scenario achieve confidentiality? And if so, why or why not?
I'd say there's not enough information. Not enough messages encrypted.
Yes, very good. So let's say that message is just a plain text.
The answer is no.
The answer is no, right? Exactly, because we're just sending the plain text. So then what do we need to do? To achieve both confidentiality and integrity, we would take the plain text, encrypt it, right? Create the cipher, and then you can take a hash of the cipher, for instance, and send that out. And then you would achieve confidentiality and integrity. Exactly. Pretty simple, right? Pretty simple. But you're going to just start bundling things and start adding more and more of the techniques. And that's where, it kind of go into what he was saying, signatures and things like that as we move forward. All right. All right. So we had defined a secure hash already. But I just want to remind you, so secure hash just basically means a message of variable length through some function to create a fixed length piece of information, which is much smaller. Okay, this is something that we will do on Thursday. Generate some text and generate the hash values. So that's the definition of a hash. Okay, and then this just provides some information that is very easy to go from message to hash, but it's very difficult to go from hash to message. Okay, so that's basically what that says. Yeah, so SHA is one of the most secure ones. And again, you can try to brute force these things or look for do analytics basically, if you'd like. And there are techniques, right? So if you guys, as your term project, for instance, you can do something like this. You say, hey, I want to figure out how to break SHA-256, for instance. And that can be a nice term project. Got it? So those are some ideas. I think this is the last of the slides. Okay, so now we're just going to go to the whiteboard and just start going over things like modes of operation, etc., more specific to algorithms, right? Because we need to implement that XOR operation for confidentiality. Okay, any questions, guys? All right, so the slides are done. So hopefully that's helpful. All right, so let's do the actually the stream cipher, what I wanted to cover. All right, so I'm going to more formally define the stream cipher, okay? And then we'll probably do some code for this on Thursday. I don't think I'll do any code today. All right, so we're talking about symmetric key encryption, right? And still that's block ciphers. We're talking about integrity also. So the ideas are symmetric encryption. Symmetric encryption. And then we've looked at basically two options, block ciphers. Block ciphers. And we've looked at that quite a bit and we've defined it a little bit formally. Right now, I'm going to define the stream cipher just a little bit more formally. Guys, any questions? I'm going to do the stream cipher. So this is, the idea basically. So this will motivate basically the pseudo-random number generator function. Okay, so we'll talk about that on Thursday. We'll go over some code to do that. But the basic idea I've already discussed, which is, what did I say about stream cipher? 1 byte at a time, right? That's the key idea. Everyone agrees? So 1 byte at a time. We have 1 byte. Yeah, let's just say 1 byte at a time. At a time. That's really how I remember it, I guess, is what I'm trying to say. This is how and I want to make the connection a little bit to the one-time pad, right? So the motivation for that. So actually, literally, this slide or discussion is sometimes called making the one-time pad practical, right? So we couldn't make it practical. Do you guys remember that was the underlying problem, right? That we needed in the one-time pad the message to be the key, to be as long as the message, and we also need the key to be fully random. So we got to give up some things. So before what we gave up is we made the blocks. We took the message and broke it up into blocks. Right now, I'm going to try a different approach. All right. So the idea in the stream cipher is to replace the totally random key with a pseudo random key. All right. So that's going to be the basic idea. So in the one-time pad, OTP, we have a message, right? ... We have a message M, and we have a key . Key, right? And then we XOR it. And we establish that as long as the key is fully random, we have actually perfect secrecy. Go to a new line. Okay. All right. So what we're going to need is a pseudo-random generator, which is a function basically, and this is called a PRG. So we'll use a library in Python on Thursday to see, unless we have enough time today, to see how that works. But we're going to be using a PRG. Okay, PRG, which stands for a pseudo-random and this is, a very important concept because it's not random actually. Pseudo-random generator. Okay, PRG. And this, we're going to establish that this is basically a function. So we're going to treat it as a function that takes, whoa, okay, sorry. Give me a second. Okay. Sorry. Okay, so this is a function. The function is going to be deterministic. So that means it's going to have a specific algorithm, but it's going to take in a seed, which can be a random number. Okay. Seed, and this is the random number. So this function, so we're going to denote this formally as G. All right, so then we're going to say that G will be a set of 0 to 1, 0 or 1 of length S. Okay, and that's basically the definition of this key that we generate from the pseudo-random generator. Okay. So S is the length, I should say. So this is the length of the key. All right, so basically then we're going to have a key which is random, as much as possible. And then we're going to have G, and G will generate because G is like an algorithm. So G given K will just keep generating bits as long as we need them to be. And in general, we're going to need them to be as long as the original message. Done. So remember, this is the pseudo-random key in essence. And this is going to be the plain text message, so we can perform an XOR operation. Does that make sense? So this is how you use the stream cipher basically to try to achieve the one-time pad. We almost got it, right? We almost got it, except what's the problem? The key is not actually random 100%. It could be 85% random, but it's pseudo random. So how do we go from a 50% pseudo random key to more random? You improve the algorithm, obviously, and that's kind of the idea, right? That people said, okay, let's just try better algorithms, etc., to achieve more randomness. But that's it. It's a simple concept, okay? But we've established it then, and we are able to perform our original operation of taking the key with the message and obtaining basically our cipher of the same. And we don't have to send all of this one at a time, by the way. Remember, we do this one byte at a time, which is equivalent. It's the same idea. Does that make sense, guys? Okay, I may ask you to implement this, so right. Keep that in mind. All right, so then just to kind of finalize here, we're going to have so the functions are going to be for the cipher E, which is the XOR operation of a key and a message, which in this case would be M XOR GK, right? So that should be obvious. And then to decrypt, we have a decrypt algorithm, just the XOR operation in its simplest form, although you can add more complexity to it. And this is going to take K, C. So this gives you C XOR GK. So both Bob and Alice will need to have the same algorithm on both ends and the key, basically, right? And then they should be able to do the communication. Any questions? Make sense? All right. What time do we have? It's 5:10. Right. Well, right. So I guess we have enough time. Let's do the pseudo-random code then. Kind of wrap up this concept. So I'm going to implement this in Python. Shouldn't be that long. Okay. I'm going to go ahead and stop sharing this. Okay. Now I'm going to do this. And I'm just going to start the virtual machine. All right, so we'll need to install maybe some things, some libraries. And I'm not going to do the algorithm here. Instead, I'm just going to give you, I'm kind of trying to give you a function that produces this pseudo-random sequence, okay? So that you could, use that. And then we're going to play with it and see what we can do with it. Log in. Okay. All right, so the logic is we're thinking of symmetric key encryption, not block cipher, but instead the other thing, which was the stream cipher, right? We're trying to approximate the one-time pad, which means that we're going to have a key as long as the message. We cannot achieve that with a totally random key. Therefore, we have to use a pseudo-random key. Therefore, we need a function called a pseudo-random generator or PRG, right? That's kind of what we've discussed. I'm going to go ahead and try to start to implement, or I'm not implementing the algorithm. I'm just going to use a library, but I'm trying to provide or have a pseudo-random generator function. Okay. So we may need to install some libraries. I'm going to go to ITS 350. Here. Yeah. All right, and in here, I'm going to create a new folder called PRG or my PRG. For pseudo-random generator. Okay. Sorry about that. All right. So we're going to create a script from numpy.random import generator. Okay. And generator is going to be an object. Let's call it RG. Right. And so we're going to instantiate this generator as RG. And then we're going to actually need to tell it an underlying algorithm that we want to use for this generator. So we can use a library also called from random gen import AES counter. Okay, so as you can see, these are we can have generators with different algorithms in them. Does that make sense? This, so you can build various approaches. Okay, so import AES counter, and both of these libraries may not be available in your distribution, so we'll have to install them. So here in the generator, we'll specify that we're going to use AES counter as the underlying algorithm. So we're going to provide some kind of a seed and then a mode, which is to generate sequences. Okay, so that's basically all we need, right? And then we can start using this pseudo-random generator. I actually should call this PRG. Got it? All right, so let's go ahead and try this out. And let's see if it breaks in some parts. So I'm going to print the PRG just to see what we get. Okay, everyone with me? So I'm going to hit Control X, Y, Enter. I'm going to try to run it. Okay, worked for me. What about you guys? Do you get errors? What does it say?
Module not found error, no module name done on line 2.
No, no, all right. So then for that, try pip install NumPy. I already have it. Probably from pip not found. Are you guys typing Python 3? Oh, pip 3. Sorry, pip 3. You guys have Python 3. Pip 3. Try that. Does that work?
Yeah.
Okay, perfect. Yeah. All right. So let me know when it finishes installing and then just run it again. Guys, did it install? Yep.
I'm getting an error from the
What-
module named random gen.
Random gen. Okay, so if the same thing, do pip 3. If you're getting that error, please pip install random gen. Okay, as you can see, these are all like libraries to provide functionality for random number generation, algorithms. Perfect, thank you. All right, so you got this, right? So the object has been created. So now this might be a nice homework, right? That I might give you guys. Oh yeah, please go ahead. What is it? Okay. Let me do this. Yeah, let me just give everyone like a command to play with, and then I'll load. All right, so just give me a sec. I'll be with you in a second. All right, so you have the PRG object, right? This is a pseudo-random generation function. So now you want to start using it to generate data of some kind, right? So what I would suggest you do is you take PRG dot random again, right? And print that out, right? And then try to print that out in a loop and just look at the behavior. What we want to do now is we have this function and we want to start in a stream cipher type of a way to start generating data. Do you guys hear what I'm saying? Right? Play with that idea. Let me. I think it needs to be uppercase.
Oh,
So open up the, yeah. That generator here, that G needs to be uppercase. It's case sensitive. Okay, I'm gonna try it myself, right? And try to generate something. I generated a number there. So let me. I'm gonna call this res. Print. Okay, so let's try that. Okay. Whoops. Zero. Okay. It's giving me the same number. So my goal is to start to generate a sequence, right? So how do we do it? One, two, one. Okay, all right, yeah, there we go. All right, so I was getting worried there. So I think it's like it's like a continuity kind of a thing. So it generates one, then it needs to generate the other ones. Do you see what I'm saying? Like, so there we go. I did 10 here, and that's basically a sequence. So if I run this again, what would you guys expect? It's the same, right? And that makes sense. That's both ends. This would be the Bob, and this is Alice, right? Because you would need that key to be the same on both ends, but it is now a pseudo-random key that you can XOR with a message. Do you guys understand? Yeah? Everyone understand? Any questions? If I ask you on the lab on Thursday to implement the one-time pad using a stream cipher with this, you'll be able to do it. So if the message is double in size, let's say the message is double in size, then that kind of implies that it's 20, right? Right? So it's longer. That's, you take the message, generate the random sequence 1 byte at a time, XOR them, send it out. On the receiving end, once you get the message 1 byte at a time, and it's the exact same one, correct? You can confirm, and therefore you effectively have 2 keys, one in, one side of the world and another one in the other side of the world, as long as you want them to be, because it's based on this technique. And the one thing that you have to keep a secret, most likely, is the 1, 2, 3, 4, 5. Right? And then effectively you can achieve a stream cipher algorithm. Okay. All right, it's 5:37, so this is a good stopping point. I'll stay for a few minutes if you guys have any questions about this idea. Look at the video if you if you want, but my goal was to give you an example of how to create a pseudo-random key. All right, that's what the whole generator thing is for. It's a little bit more random than you think. Just not 100%. All right, guys, see you Thursday.